This is problem number 5A on the sample test problems for test number 3. Solve each of the following problems. Relate the rates. Newton and Leibniz have met in the desert to discuss their research. Newton leaves at noon and drives north at 60 miles per hour. Leibniz spends some time finishing a problem, then leaves at 1 p.m. and drives east at 50 miles per hour. At what rate is the distance between the two mathematicians changing at 2 p.m.? Lots of stuff going on in this problem. I'm just going to call your attention to one word: distance. So we're going to be writing down some distances as we set this up. A picture seems appropriate, so let's go ahead and draw a picture. Newton is going to go north, so we'll have Newton start. Newton and Leibniz will both start there. Newton is going to go north, and if we know that Newton is traveling at 60 miles per hour, I feel like I can write the distance right next to this thing. So if t is the number of hours that we've been going, t for time, then Newton's distance from the start is going to be 60t. And then an hour later, Leibniz leaves and heads east. I'm going to draw that one shorter. Number one, he started late, and number two, he's driving slower. So I don't know that it's to scale necessarily, but certainly it's going to be shorter than the other distance. Based on the given information, we know that Leibniz is traveling at 50 miles an hour, so it's going to be 50t, except we got to deal with that head start. So the fact that Leibniz spent an hour finishing that problem means he had one less hour or one fewer hours to travel. So it's actually 50 times t minus 1. Leibniz was only traveling for t minus 1 hours, one less than Newton. Okay, and we've almost got a pretty right triangle, so why don't we just go ahead and connect the dots and finish the right triangle. And we're looking for the rate at which the distance between these two guys is changing, so it seems like we're going to want to give that thing a name, because I want to find the rate at which that distance is changing. So I'm just going to highlight what we're given and what we want at the instant in time we're focusing on. So we're going to find the rate at which the distance is changing. So symbolically, that's a dc dt. And it says at 2 o'clock. And so for me, we started this problem at noon. So that's t equals 2. I'm not going to plug t equals 2 in until the end. So first we need an equation that relates everything in this picture. It's a right triangle where we've got the 3 side lengths. That's Pythagorean theorem. So writing Pythagorean theorem out, we know that one side squared, don't forget parentheses, plus the other leg squared is equal to the hypotenuse squared. So that's our equation. And that's it, frankly. You could just take a derivative right now. I'm going to choose to clean this up a little bit before I take a derivative, but you're perfectly welcome to leave it as is and take a derivative. What I'm going to do is square this first guy, so that's a 3600 t squared, plus, and then maybe pause the video. I'm going to encourage you guys to just take a minute to distribute the 50 and then square. So you're going to be foiling after you distribute. So pause the video and come back when you're ready. So hopefully after you've done those two things, you get 2500 t squared minus 5000 t plus 2500. And that's still equal to c squared. And then finally, these two terms combine. They're both t squared, so let's mush them together. And we get 6100 t squared, and we'll copy everything else. So that's our equation. And now we're going to take a derivative of both sides. But we got to be clear what we are taking a derivative with respect to. In just about every related rates problem, the underlying variable is time. So we're going to take a derivative of both sides with respect to time. Just wanted to have a little more space to write that derivative symbol. So both sides get hit with a d dt, derivative with respect to time. So on the left-hand side, looking for the derivative of 6100 t squared. All right, so the 2 comes down, hits the 6100, so we get 12,200 t. And then do we need to stick anything next to this? And the answer is no. T is the underlying variable, so you don't need to put anything here. Minus, what's the derivative of 5000 t? Just 5000. The derivative of the plus 2500 is nothing. Equals, the right-hand side is a place where some folks get tripped up. The derivative of c squared, 2c, no problem. But c in my mind is a function with t's floating around in it, and so the chain rule rears its ugly head and says multiply by derivative of the stuff. The stuff is called c, and the derivative of that is dc dt. It's okay to call it C prime, but I prefer to really be explicit here because we've got all these letters floating around. All right, so now I think we have our equation. Remember again, the goal was to find dc dt. So as soon as we find dc dt, we're done. So that's what we want, and finally it appears. So apparently everything else in that equation is going to get replaced with numbers. So let's start replacing. 12,200. The t that we're given in this problem is 2 o'clock, 2 hours. That's the first place we can plug the t equals 2 in. Don't do it any earlier. You got to make sure you take a derivative first before you plug in the t value. Minus 5,000 equals 2 times, all right, there's a c. I don't quite know what to put there, but I'll just put a blank, and then times dc dt, that's the thing we're after. So this problem boils down to just being able to figure out the value of c. So c, remember, is, so start highlighting. So we're after the c, we're going to fill in whatever we get over here, and the c fundamentally appears right there. So if we can somehow find the value of c when t is 2, then we'll have it. So I'm going to squeeze another right triangle right here. This right triangle is going to be fixed when time is 2. And so I'm going to plug time equals 2 into that equation right there. So 60 times 2 is 120. So that means that Newton has traveled 120 miles. Plug the same t equals 2 in there, and you'll see that Leibniz has gone 50 miles. So that's a 50. And now to find c, well, do the Pythagorean theorem again. I suppose we could have just plugged into this equation right here in purple, make all those t's equal to 2. That's fine as well. So do your Pythagorean theorem, and hopefully we get c is equal to 130. So c is 130 from another Pythagorean theorem. Okay, and then I think we're good. We just have to do a tiny bit of algebra and a little arithmetic to solve for dc dt. So 12,200 times 2, and then subtract 500, and then divide by the 2 times 130. So I don't have any more room, so I'm just going to type this in as it is. But if you have some space, maybe do a little more writing before you type. So we're doing 12,200. It's going to get doubled, and then we're going to subtract 5,000. So this is the whole left-hand side, and then we'll divide by the 2 times 130. Real easy to make this mistake. This will give me the wrong answer, and I probably won't catch it. 2 and 130, either multiply them first separately or put parentheses. So dc dt is 74.615. Squeeze it in down here. dc dt 74.615 miles per hour.